All right, I just want to take a minute to focus on interpretations. And so this may be a review of some previous statistics classes, but it's always important to sort of make sure that we're grounded in the correct interpretation of all of these different pieces. A big part of this class is deriving these different kind of underlying formulas that are really integral to statistics. And so we spend a lot of time on deriving those formulas. But it's really important that once we have those derived formulas that we actually understand what the output means and how to interpret it in an applied practical setting. And so that's what this short section is focused on. And so the first thing I want to focus on is how do we interpret beta hat in multiple linear regression? And so this is how you would interpret it. You would say the coefficient for x, so some predictor, is beta hat. And then it's always good to also mention the 95% confidence interval, which in the next class we're going to be talking about how to actually derive that and to interpret it correctly. So you'd say the coefficient for predictor x is beta hat with a 95% confidence interval of lower bound, upper bound. This means a 1 unit increase in the predictor x yields an expected increase in y of beta hat, holding all other variables constant. And so all of this is very, very important, but especially this holding all other variables constant in multiple linear regression, those beta coefficients are interpreted in the context of the other variables. So here's some output from R for the hitters data that we've been using a lot in the lab and in the previous lecture. And so I'm fitting that same model. I'm predicting salary from the at-bat and hits variables. And this is the output that I come up with. And so the way that I would interpret this here, this value is for every time at bat, for a 1 unit increase in that at-bat variable, we expect that y will have an expected change of negative 1.21, holding hits constant. So holding the number of hits constant. And similarly for hits, a 1 unit increase in hits will yield an expected change in y, so an expected change in salary of 8.2, holding at bat constant. And what about the interpretation of this intercept? So the intercept tells us what we would expect salary, so what we would expect our outcome, our y variable to be, when all of the predictors are 0. So if the number of times at bat and the number of hits for a player were both equal to 0, we would expect the salary to be 141.27 on average. Okay, the next piece is the standard error. So the standard error tells us how much we expect the sample slope, or in the case of, so if it was just simple linear regression, it'd be the sample slope. In the case of multiple regression, it's going to be the beta coefficients to vary from one random sample to another. And so in this case, our standard error that we're seeing here for at bat is 0.632372. And our standard error for hits is 2.0799. And those standard errors, it's important that basically they are letting us know how much we would expect these numbers to vary in a new random sample. And they need to be somewhat grounded in the actual values that we're seeing for the beta coefficients. And so a really common way to be able to sort of ground the relationship between the beta coefficients and the standard error is to take the ratio between the two of them. So divide the estimate by its standard error to get this kind of comparable number that you could compare regardless of the scale. And so that's exactly what a t-value is. That's what the t-statistic is. It's just the beta coefficient divided by the standard error. And so in this case, for hits, 8.2 divided by 2.0799 is equal to 3.948. And similarly for at bat, negative 1.216 divided by 0.6372 is equal to negative 1.908. And those values themselves, those t-values, are compared to a t-distribution, and under the null, we would expect this to have these to have a t-distribution, these statistics to have a t-distribution with n minus p plus 1 degrees of freedom. And so we can use that information to calculate a p-value. Similarly to how we used the information from the F distribution to calculate a p-value for our F statistic, we can use the information from the t-distribution to help us decide the probability of seeing a result as extreme or more extreme given the null hypothesis is true. And so that brings me to the next part here, the p-value. So the p-value is the probability of getting a statistic as extreme or more extreme than the observed test statistic given that null hypothesis is true. And so again, that's what these values are here. So for example, hits, the probability of seeing a statistic as extreme or more extreme than 3.948 given the null hypothesis is true, where the null hypothesis here is that the estimate is 0, so that this beta coefficient is 0. And that probability, given the null hypothesis is true, is 0.0001. So it's pretty small. And so that if we were using an alpha cutoff of 0.05, so if we were comparing this p-value to 0.05, we would reject the null hypothesis, basically saying that the beta coefficient is not 0. So we would reject the null hypothesis saying, the beta coefficient is 0. So we're rejecting that null hypothesis that the beta coefficient is 0. Now for this at-bat variable, we can do the same thing. We can compare this negative 1.908 to the t-distribution under the null and see what the probability would be for that. So that would be, we're testing now the probability that this beta coefficient for at-bat, that beta 1 is equal to 0. So that's our null hypothesis, and the probability that we would see a statistic as extreme or more extreme than negative 1.908, given that null hypothesis is true, is 0.05743. And so if we were using the common alpha cutoff of 0.05 to compare this p-value to, we would fail to reject this null hypothesis because this is slightly larger than that alpha value. And so we would fail to reject the null hypothesis that beta 1 is equal to 0.